Welcome to the unit on cellular respiration. In this unit, we will be discussing the details of cellular respiration, an important catabolic reaction that converts energy in fuel molecules to ATP. We will divide this chapter into three main topics: an explanation of oxidation-reduction reactions and their connection to cellular respiration, the details of cellular respiration metabolic pathways, and a description of fermentation and other catabolic reactions. Let us start with oxidation and reduction reactions. The overall process of cellular respiration converts the potential energy stored in the chemical bonds of carbohydrates, such as glucose, to potential energy stored in ATP. By doing this, the carbohydrate is oxidized to carbon dioxide. The overall chemical formula for cellular respiration is glucose, which is C6H12O6, plus 6 oxygen yields 6 molecules of carbon dioxide plus 6 molecules of H2O plus 32 molecules of ATP. During cellular respiration, ATP is generated using two different mechanisms. The first is called substrate level phosphorylation, in which an enzyme-substrate complex is used in a hydrolysis reaction that releases energy to drive the synthesis of ATP. This produces a small amount of ATP for the cell. The second process uses energy in electrons transported by electron carriers to the electron transport chain. During the transfer of electrons, energy is harvested to produce ATP. This is called oxidative phosphorylation and produces the majority of ATP in cellular respiration. Cellular respiration is based on a series of oxidation-reduction reactions, which are reactions that involve the movement of electrons. Molecules that have been oxidized or gone through an oxidation reaction, such as A, have lost electrons. Molecules that have been reduced or gone through a reduction reaction have gained electrons. Oxidation and reduction reactions are coupled together because when electrons are lost from one molecule, they must be transferred to another. An easy way to remember oxidation-reduction reactions is to remember the saying that Leo the lion goes grr. Leo for lose electrons oxidize, and grr for gain electrons reduce. When you examine a chemical formula, you can determine what molecules have been oxidized and which have been reduced by following the presence and absence of hydrogen atoms. Keep in mind that a hydrogen atom is 1 electron and 1 proton. In the cell, there is a supply of free protons, so an electron is transferred, it often attracts a positively charged proton, forming a hydrogen atom. We can observe this in the equation for cellular respiration. Here, glucose is oxidized to carbon dioxide, notice the presence of hydrogen atoms in glucose and the lack of them or the loss of them in carbon dioxide. The electrons removed from glucose are eventually transferred to oxygen, causing oxygen to be reduced to water. Again, notice the presence of hydrogen in water and its absence in oxygen. Because it gains electrons, the oxygen atom is the electron acceptor, and the glucose is the electron donor. Because oxygen accepted the electrons, allowing glucose to be oxidized, it is called the oxidizing agent, while glucose is considered the reducing agent. You have likely observed very rapid oxidation of glucose to carbon dioxide. This reaction occurs every time you see a fire burn. However, the energy released during oxidation is released as light and heat energy. The cell must have a way to oxidize glucose much more slowly so that the released energy can be captured to do cellular work. This is accomplished by using a series of enzymes to oxidize glucose in a slow, controlled manner, which allows the capture of energy by ATP and electron carriers. The two key electron carriers in the cell are NADH and FADH2. These are the reduced forms of NAD+ and FAD. During cellular respiration, NAD+ or FAD picks up electrons, seen here in these two equations, during the oxidation of glucose. They are then reduced, and these electron carriers will bring those electrons to the electron transport chain, where they will act as electron donors, becoming oxidized back to NAD+ or FAD. You should note that they each carry 2 electrons. In NAD, the first electron cancels out the positive charge, while the second electron is viewed as the addition of the hydrogen atom. In FAD, since there is no positive charge, both electrons bring in protons, resulting in the addition of 2 hydrogen atoms. The oxidation of glucose is an exergonic process, thus it has a negative delta G. The slow oxidation of glucose allows that released free energy to occur sequentially over small amounts, which are then captured in either ATP or NADH and FADH2. Notice that the free energy of the overall process of cellular respiration goes up. This is equivalent to the activation energy for the process. At each major drop in free energy, the released energy is transferred to the electron carriers. These reduced form of electron carriers have a high potential energy that they use to synthesize ATP through oxidative phosphorylation in the final stage of cellular respiration. There are 4 stages in cellular respiration. The first 3 are labeled along the top, being glycolysis, pyruvate oxidation, and the citric acid cycle. The 4th is the electron transport chain, in which the electron transport molecules will eventually travel. These stages of cellular respiration will be discussed in the next videos.